We are fighting a daily war against cancer. But do you even know where that actual battlefield of war is? It is not the organ. It is not even the cell. The ultimate battlefield is the atom. Yes, atom. But here is the most bizarre secret in physics. If you make an atom the size of a massive football stadium, the nucleus is just a tiny grape sitting right in the center. Everything else is completely empty space. If there is so much of empty space, how does radiation actually hit anything? How does an X-ray photon find its target in all that empty space? If you do not know the exact structure of this stadium, basically atom, you cannot master radiation physics. Today we are going to form the absolute foundation and look at the atom in detail. For most of you, this topic may sound too basic, but I want to teach you this from a radiation oncology perspective. We will not study it like how a 12th standard student reads it. Hello friends. Before we begin, for those who are new to this channel, I am Dr. Parveen Ahlawat. I am a consultant at Rajiv Gandhi Cancer Institute and Research Center in New Delhi for over 12 years. I have been practicing and teaching oncology for more than a decade. I did my MBBS and post-graduation from CMC Vellore. Then I did my DNB at Rajiv Gandhi Cancer Institute and Research Center, New Delhi. I pursued a fellowship at the Royal Marsden Hospital in London and have later undergone specialized training in cyberknife from the United States. I have published almost 85 research articles and abstracts in PubMed Index international journals. Our topic for today's discussion is atomic structure, and more importantly, what keeps an atom stable and in equilibrium state. How are the X-ray born? If you have watched my previous videos, we learned some basics of physics. We broke down the exact definition of radiation and learned the exact meaning of every single word in the definition of radiation. We classified the various types of radiation. We also explored the entire electromagnetic spectrum in clinical detail. Today, I am going to teach you where exactly this radiation comes from and what it strikes. Let us begin. This is an atom. I want you to look very carefully at the numbers written here on this slide. The total size of an atom is roughly 10 to the power of minus 10 meters. 10 to the power of minus 10 meters. It is so very tiny. But the central nucleus is even much smaller than that. The size of the nucleus is only about 10 to the power of minus 15 meters. This means there is 100,000 times difference in their size. Let me give you a perspective of these relative sizes. If an atom is a massive football stadium, can you guess what the size of nucleus be? Not even the size of a football. The size of the nucleus would be the size of a single grape. Just imagine one grape kept in the center of this massive football stadium. Are you not shocked? Because of this huge difference in size between the atom and the nucleus, an atom is actually mostly empty space. It is just a lot of empty space in the center of which you have a very dense central core. Now let us look at the components of an atom. Right in the center of this atom is the nucleus, which contains the positively charged protons and neutral neutrons. And very far away from this core are the negatively charged electrons, which are revolving in their specific defined circular paths called called orbits or shells. This arrangement is very similar to how various stars and our Earth rotates around the Sun. So basically there is a lot of empty space within this atom. The actual space occupied by nucleus and electron revolving around it is actually very small. Why knowing that there is such a large vast empty space between nucleus and surrounding electrons in an atom is so important for us? Look, when an incident photon of a radiation enters the patient's cell, it travels through this exact empty space. The chance of a radiation beam hitting the nucleus or electron depends entirely on this massive size difference. This basic physical layout dictates every single photon interaction we will study today. Here we are closely looking at the exact paths where these electrons live. These specific paths are known as the orbits or shells of the atom. Orbits or shells. You see that these orbits are named with letters. We start from the inside near the nucleus and move outwards. The very first shell is the K shell, followed by L, M, N, O, P and so on. Each of these orbits or shells is given a simple number called the principal quantum number. We write this number as the letter n, small n. So, for the K shell, number given is 1. For the L shell, number given is 2. For the M shell, the number given is 3 and so on. Now, how many electrons can actually fit inside each of these specific orbits? We do not just guess this number. We calculate it using a very simple mathematical formula. The formula is 2n to the power of 2. Look at the table here. For the K shell, which is the innermost shell where n equals 1, we put 1 into the formula. This calculation gives us exactly 2 electrons. That means the maximum electron capacity of K shell is 2 electrons. For the L shell where n equals 2, the formula gives us 8 electrons. That means the maximum electron capacity of L shell is 8 electrons. And for the M shell where n equals 3 can hold up to 18 electrons. And in a similar way, you can calculate for shells N, O, P, etc. We observe a special thing here. As the physical distance of any shell from the nucleus increases, the maximum electron capacity of the shell expands, but not linearly. It increases exponentially. This exact physical arrangement determines how an atom will interact with our radiation beam. This slide shows exactly how we represent an atom in physics. The large letter X represents the actual chemical symbol of the element. For example, we use the letter C for carbon, O for oxygen. The letter Z in subscript shows the atomic number. It tells us the exact number of protons inside the nucleus. I want you to remember this next point very clearly. The atomic number is the absolute identifier of any treatment. The atomic number is the absolute identifier of any element. If you change the number of protons, the element changes entirely into a different substance. The letter A in the superscript shows the mass number. Mass number is the sum total of all the protons and neutrons together. You can think of it as the total physical weight of that dense central core. Now listen to me very carefully. In the center of the atom is the massive positively charged nucleus. Outside, negatively charged electrons fly around in their orbit. But wait. We know that negative charge always attracts positive charge. If this is really true, why do these negatively charged electrons not simply crash directly into the positive nucleus? Or why not these electrons just fly away into empty space? What keeps an atom and its component completely stable and in equilibrium? This perfect atomic balance or equilibrium is maintained by a set of two invisible forces. The first force is between negatively charged electron and positively charged protons, which keep a constant inward pull of electron towards nucleus. Or you can say the positive protons inside the nucleus constantly attract the negative electron. This inward force or attraction is called as electromagnetic force. Electromagnetic force. But at the exact same time, there is another force which exists called as centripetal force. Centripetal force. The electrons, even though are revolving around the nucleus in their orbits, have a forward momentum because of their continuous orbital motion, like this. This forward movement perfectly counters that inward electromagnetic pull. Once again, this forward movement perfectly counters that inward electromagnetic pull. This perfectly balanced tension is what holds the entire atom together. Because of this exact balance, the electron is prevented from falling out of its orbit. We must understand this balance of forces right now to understand our next topic, binding energy. This slide introduces a very important concept called binding energy of an electron. Binding energy. What exactly is binding energy? It is the exact amount of energy required to eject an electron completely away from the atom. Once again, it is the exact amount of energy required to eject an electron completely away from the atom. This binding energy depends on two main factors. The first factor is the physical proximity of the electron to the nucleus. How close the nucleus is to the electron is to the nucleus. Look here in this atom. This is nucleus, and these are various electrons in their respective orbits. In this atom, two electrons are shown for simplicity. One electron is very closer to the nucleus and the other is far away from the nucleus. Please notice that the closer the electron is to the positive nucleus, the stronger the grip. Once again, the closer the electron is to the positive nucleus, the stronger the grip. Because of this very close distance, electrons in the innermost K shell always have the highest binding energy. The second factor is the total number of protons inside the nucleus. These are two atoms of different elements. These are the nucleus of these two atoms. Since lower atom has a higher number of positive protons and thus larger nucleus, it will have a much stronger inward pull for the electron. More positive charge simply means a stronger attraction. The upper atom has fewer protons in the nucleus and thus a smaller nucleus. Hence, it will have a much lesser inward pull for the electron. So that means heavy elements with many protons have a very high binding energy. We have seen the perfect balanced forces. We have seen the incredible grip the nucleus has on its inner electron. But why must we learn this for radiation physics? Because to create our clinical weapons, X-rays, photons, we must break that perfect balance. We must eject an inner shell electron from its orbit. Look at the tightly bound electron. The thick black arrow shows a large inward pull from the positive nucleus. This electron is trapped in its place and cannot be ejected out. It is locked in place by its specific binding energy. It will not simply fall out. So how do we break it free? We must strike the atom. An incoming wave of pure external energy violently hits the electron. But it cannot be just any weak amount of energy. For ejection to happen, it has to be of high energy. To speak precisely, applied energy must be greater than binding energy. If the incoming strike is even slightly weaker than the binding threshold, the electron stays trapped and cannot be ejected out. The incoming energy must be massive enough to completely overwhelm the grip of the nucleus. Look here, the impact is successful. The applied energy is greater than the binding energy. The electron is blasted out of its orbit and into empty space. But what is left behind? Look closely at the dashed circle. A vacancy. Vacancy. We have created an empty, highly unstable hole in the inner shell of the atom. This single event is everything. Overcoming the exact binding threshold, ejecting the electron, creating that unstable vacancy. This exact event is the absolute genesis of generating characteristics X-ray. When an outer electron drops down to fill that empty vacancy, our clinical X-ray photon is born. Please burn this fundamental mechanism into your memory before we proceed further. So friends, with this we finish our short lecture today. If you have watched my previous video, I taught you what is the definition of radiation. I also showed you exactly what it is. I classified it. I showed you the entire electromagnetic spectrum. Today we looked at the absolute foundation of matter. We looked at the atom. We saw the invisible equilibrium that holds it together. Most importantly, we learned how to break that balance. We learned how to overcome the binding energy. This brings up a big clinical question. Where do we get this external energy from? How do we fire the bullet to eject that electron? We need a machine for that. In my next presentation, I will step out of the microscopic world of the atom and move into the clinic. I will take you deep inside the X-ray tube kept in your radiology department and radiation oncology department in linear accelerator. We will see how we generate a large cluster of electrons. We will accelerate them to high speed, and then we will smash them into a heavy tungsten target. What happens then? In the class after that, we will look at the aftermath of that collision. We will witness the birth of our clinical X-ray beam. This happens through Bremsstrahlung and characteristic radiation. As you now know, characteristic radiation is born directly from the atom trying to fill that vacancy. I will see you next session. Thanks for watching. Signing off, Parveen Ahlawat.